Okay, so now you understand the intuition that we just want to look at the k cases which are nearest in some sense to the case we are trying to classify. Once we found that, we just go by the composition of those k cases. Very simple. But the difficult part here is, how do you operationalize this intuition? What do you mean by similar? What do you mean by closest? That's really what we want to get at this point. Okay, so again, just to look at it, we've got another data set. Target attribute is here, and these are two predictor attributes. So the task is, along comes somebody else whose income we know, whose number of cars we know. Those are the two predictor attributes. We want to find out whether this person is going to be a owner or not, yes or no. Those are the two classes. But we can define that or decide upon that only by finding the neighbors, right? The k nearest neighbors. So let's assume we know the value of k, like 3 or 5 or something like that. I'm not choosing even numbered values because then you could have a tie between the two classes, especially in the case when your target attribute has two classes. You don't want to choose an even number because in the case of a tie, you cannot resolve. Okay, so it could be k equals 1, 3, 5, 7, 9, 11, whatever, right? So that's what we're looking at. So clearly, we have to find out which are those k cases which are closest to this particular given case. Okay, so here you've got a particular case, and here you've got a new case. So this is just the first case, right? Because after all, in order to find the k nearest neighbors for this, you have to find the distance from this to all of the other cases, and then find out which are the k of those. Let's say k is 3. Which are the 3 of those which are closest? Okay, which means you have to calculate the distance from this to each of these cases. So I'm considering one case, the first case. Okay, so we are given a person whose income is 85,000 and who has 2 cars. And we want to compute the distance from here to a person whose income is 95,000 who has 1 car. Okay, of course, the target attribute doesn't play a role at this point in time. We're just trying to find the distances and identify the k nearest neighbors. Okay, so how do you find this distance? Now, one way you can do it is you can use literally the distance formula, right? So think of this 85,002 as a point with the x value of 85,000 and y value of 2. So it's like a point on a graph. And 95,001 is another point on a graph. And think of the distance literally as the distance between those 2 points. This is referred to sometimes as the Euclidean distance, right? You're literally drawing geometric shapes on paper on a 2-dimensional surface and computing the distance. So that would be obviously the difference between these two squared plus the difference between those two squared, and take the square root of that. That's what is the distance. Okay, so the intuition is something like this, right? So think of income as being on the x-axis, number of cars as being on the y-axis, and so these are the 2 points. Let's say this is 85,000 income, 95,000 income, and 1 car, right? So this represents this point, 95,001, and this represents this point, this point. Income is lower, 85,000, but the number of cars is higher, 2. Okay, so that's what we are trying to do. We are trying to calculate literally the distance between these two. And of course, the distance between these two is nothing but if you draw the right angle triangle, right? So this is the difference in income, 95,000 minus 85,000. That's what this is. Okay, and that is nothing but the difference in the number of cars, which is 2 minus 1. That's what this distance represents. So this obviously, if you apply the Pythagoras theorem, this is a right angle triangle. You can say the distance that the hypotenuse squared is nothing but this square plus this square. That's exactly what this formula is telling you. Okay, so we are simply applying the distance formula to compute the distance between any 2 cases, right? So now that we have defined distance, it's pretty straightforward for us to go back and take this case, compute the distance to all of the cases in your training partition or whichever partition, right? So compute the distance to all of them and choose the k distances which are smallest, k being 3 or 5 or whatever. Now you may be wondering at this point, wow, if I have a data set with 10,000 rows or a million rows, that's a lot of computation. Yes, it is a lot of computation, but we are not going to do the computation. The computer is going to do the computation. And it turns out that, you know, even for very large data sets, this is not going to take a lot of time. Okay, so that computation part is not an issue unless you go into millions and millions of rows. Then it could be an issue, and we need to think about how that can be handled. Okay, so this is the idea. So we have now given an operational definition of what do you mean by similar. Similarity is nothing but distance, right? The smaller the distance is, the more similar two cases are. The larger the distance is, the less similar the cases are. Straightforward, that's it. Okay, but it turns out there's still a small problem with this, which we will look at just now. Okay, so first important point to understand is when you're using KNN for classification, of course, you're talking about classification. Therefore, the target attribute has to be categorical, right? Because otherwise, why would you use something for classification? Because your target attribute is categorical. That is straightforward. But the important point is, since we are computing distances, our predictors have to be numeric. Okay, if the predictors are not numeric, then we cannot use KNN because calculation of distance requires things to be numbers, right? All of these things have to be numbers, otherwise how can you calculate these things, right? So that's an important thing. If you want to use KNN for classification, of course, the target has to be categorical and predictors have to be numeric. All predictors have to be numeric. Okay, now, of course, as I have already pointed out, KNN technique is also applicable for regression, but we'll discuss that later, not right now. So let's take a look at how this thing is going to work. Okay, so we go back to our old case of 85,002, and then we are calculating its distance from 95,001. So if you actually calculate the distance by applying the formula, it will come out to 10,000. Okay, that is because the difference between these two is 10,000 and the difference between these two is 1, right? So square root of 10,000 plus 1 is square root of 10,001, which is 10,000 squared and 1 squared. So 10,000 squared plus 1, the square root of that is going to be very close to 10,000. Okay, now suppose you consider another case. The income goes up by 50. Instead of 95,001, it's 95,051. Okay, which means what? That the income increased by a very, very small amount, because over 95,000, an increase of 50 is almost nothing. Okay, so very small increase in income, and this is of course remaining the same. Now you'll see the distances of course become 10,050, right? Because that's the difference between these two, and this is controlling it. Okay, so small change in income is reflected almost verbatim in the distance. Okay, now let's do one thing. Let's change this from 95,001 to 95,003. Okay, that's a huge increase in the number of cars. Okay, so now if you calculate the distance, it's still coming out as 10,000. Okay, that means the huge increase in the number of cars didn't make any difference in terms of the distance. Okay, it's still 10 because the difference between these two is still 1, and it doesn't play a role, whereas this is playing a role. Okay, in fact, if you increase the number of cars not to 3 but to 5, which is a huge jump from 1 to 5, right? But the distance doesn't even budge. It is still 10,000, right? So what it's telling you is that the distance between these two cases is 10,000, and the distance between these two cases is also 10,000. Okay, we would expect that there's a big difference, but that difference is not showing up. Okay, so what is happening is that the distance is insensitive to the number of cars. It is sensitive only to the income. The number of cars is not playing any role. It will start playing a role once you start having numbers like 50 and 60 here, but which is not realistic. Nobody's going to have 50 cars. Okay, so this, because of the magnitude of the numbers, because income is measured in such large numbers, it is completely dominating the computation of distance. Okay, so which is not good, because then closeness will be defined only by income, and if two people are very similar in the number of cars and two people are very dissimilar in the number of cars, that will play no role at all. Everything is going to be decided based on income alone. okay, which is not good. Okay, so that's the problem with what we have looked at so far. Okay, so there are two ways to handle this issue. One way is, instead of using the income and age, instead of number of cars, I'm showing age here. Instead of using income and age as they are, what we want to do is to change the values somehow so that they become commensurate. Right? These two values currently are incommensurate. This is too big in general, and this is much smaller. But we want to make them commensurate, so we calculate the mean of each of these attributes, calculate the standard deviation of the attributes, and then we calculate something called as the z-value, which is, for any value, subtract the mean and divide by the standard deviation. Okay. Now, of course, we understand that when you calculate the mean is sort of in this somewhat in the middle. Median is exactly in the middle, but the mean is sort of in the middle, right? So for every value, we are taking its difference from the mean and dividing by the standard deviation. Effectively, what z-value is telling you is, for any given value, how many standard deviations away is it from the mean? If it's positive, it means it's higher than the mean. If it's negative, it'll mean that it's lower than the mean. Okay, so then you're just computing and saying, for any given value, how many standard deviations away is it? Okay, so you'll do the same thing for income, you'll do the same thing for age, and even for age, you will calculate the mean standard deviation and calculate for any value how many standard deviations away is it from the mean. Okay, then the actual magnitude will not matter anymore, right? Because you're dividing by the standard deviation. The standard deviation is quite a high number. Because these numbers are high, the standard deviation would be high, right? So when you divide it, then both will become commensurate. Okay, because you're only saying for a given value, how many standard deviations away from the mean is it? This technique, computing z-value, is called normalization or standardization, right? So these are referred to as standardized values. Once you calculate this for all of these, you refer to them as standardized values or normalized values, right? We call them normalized because it sort of reflects the normal distribution in some way. Okay, it's used a lot in normal distribution. Okay, so here is an example. Here you've got a value which is 100 and the mean is 80. Okay, if you calculate, then the standard deviation is 10. So this value 100 is 2 standard deviations above the mean, right? Because standard deviation is 10, 80 to 100 is 2 standard deviations. On the other hand, you have another attribute which is measured in much smaller scales. So x is 10, mean is 8, and the standard deviation is 1. Right? So this is absolutely speaking much smaller than this, the magnitude wise. But if you calculate the z-value, it also turns out to be 2. So this 10 is 2 standard deviations away from 8. 100 is 2 standard deviations away from 80. Right? So if you standardize both of these, both of them will turn out to just become 2. So the big difference that you have between 100 and 10, that vanishes. Okay, so that's the idea of standardizing or normalizing the value. So basically, the z-value is nothing but the number of standard deviations away from the mean that any given value is. So if you take this example, the normalized or standardized values will look like this. Okay, so just think about it a little bit. It's very easy. Why is this value negative? Right? Why is the first value negative? The first value is negative. Again, I would suggest that you take a look at this, pause the video, and then continue the video once you have answered it. Okay, I assume you paused the video and continued. The first value is negative and it's not positive because the mean income is 44,462. The income for the first value is 25,162. It's below the mean. So obviously, when you do x minus mean divided by standard deviation, that x minus mean will become negative. 25,000 minus 44,000. Okay, that's like minus 19,000 divided by the standard deviation. And that turns out to be minus 2.22. In other words, this value is 2.2 standard deviations below the mean. Okay, this value, on the other hand, is 1.4 standard deviations above the mean. Right? Now, if there is a value in this data set which is exactly equal to the mean, There is no such value. If there were such a value, then its z value would be obviously 0, because it is exactly at the mean. It is 0 standard deviations away from the mean. Okay, so the value that seems to be closest to the mean is this one, 43,789, and for it the z value is very close to 0, minus 0.08. Okay, so same thing has been done for age as well. For every value, you've subtracted from the mean and divided by the standard deviation. So for example, 45 has a z value of 0.66, which tells us that it's above the mean. It's a positive value, and it is 0.66 standard deviations above the mean. You got that by saying 45 minus 37.5, which is about 7.5. It is 7.5 divided by 11.3. It turns out to be 0.66. Okay, so that's the idea here. This formula has been applied to each of these, and you got the standardized values. Notice that here the income numbers are much higher than the age numbers, whereas here that magnitude disparity has disappeared. Both of them are simply small numbers which average at 0 and whose other values are just 1 or 2 standard deviations above or below the mean. That's it. So effectively what we've done is we've taken two attributes whose values were incommensurate, meaning not capable of direct comparison. Right? It's like comparing apples and oranges. They were incommensurate, but by converting them or standardizing or normalizing them, we have made them commensurate. Right? We can now compare and say this person's income is way lower than the mean, whereas the person's age is above the mean. Right? So you can really talk about their income and age. With respect to income, they're below the average. With respect to age, they're above the average in terms of the number of standard deviations and so on. Okay, so that's the idea here. There's another option. This standardization is not the only option. There's another option also to make the two to make them commensurate. Here what we are going to do is for each attribute we are going to find the maximum and minimum, and all we are going to do is to adjust these values such that the smallest value becomes 0 and the largest value becomes 1. Right? So the range for income will become between 0 and 1, and the range for age also will become between 0 and 1. Right? So they'll become completely commensurate. And you will do that by calculating x minus min divided by max minus min. Right? So x minus min will be how far away from the minimum it is, divided by max minus min, which is the overall range. Okay, and of course if the value is the minimum, then x minus min will become 0, and therefore it will get scaled to 0. And if the value is the maximum, max minus min divided by max minus min, that will become 1. Right? So the largest value will become 1, the smallest value will become 0, and all the other values will fall proportionately in between. Okay, so that's it. So once again, you can see, of course, this 25,162 happened to be the minimum, so it became 0. And 56,680 was the maximum, it became 1. And the other values are all in between. Okay, turns out it looks like all the incomes are arranged alphabetically here. Not so with age. Okay, so same thing has happened. So this is another option. You could use either this or you could use scaling. Okay, it doesn't matter which one you use. Both of them will make the values commensurate. But of course, in a particular problem, you should stick to one of them. In other words, you shouldn't apply one method for one attribute and a different method for a different attribute. That would not make sense. So as we said, rescaling would scale the values to the range 0, 1. The minimum will become 0, the maximum will become 1 for every attribute separately. Okay, so if you're using KNN, K nearest neighbors, either for classification or, as we will study later, regression, you have to normalize or rescale all the predictor attributes. Otherwise, one or two of these attributes may dominate distance calculations and will not get good results. So now the next lesson will take a look at, well, what if I have a data set in which the attributes are not numeric, meaning the predictors are not numeric? Does it mean that I cannot apply a KNN technique for that? Or are there some workarounds? Of course, the answer is we're not stuck. There are methods, and we'll look at those methods just now.